Hello everyone, I am Rutvik Gunde and I with my colleague Shreyas Kanjalkar will be talking on computational geometry problems. To be specific, we both will be talking on art gallery problem and traveling salesman problem. I will address the art gallery problem and Shreyas will talk on traveling salesman problem. So let's get into it. So what is art gallery problem? Art gallery problem is a problem in computational geometry to determine minimum number of guards that are required or are sufficient to cover or see every point in the interior of an art gallery or a museum. So before we get into more details of art gallery problem, let's understand some important terms. So firstly, what is convex polygon? A convex polygon is a simple polygon such that for every 2 points, namely P and Q on the boundary of that polygon, no point on the line segment PQ is strictly outside P. So basically, all the angles in convex polygon are non-reflex. Then we move to the monotone polygon. A polygon P in the plane is called monotone with respect to a straight line L if every line orthogonal to L intersects P at most twice. Then we move towards triangulated graph. A planar graph G is said to be triangulated if the addition of any edge of 2G results in a non-planar graph. So basically converting a polygon into small triangles is nothing but a triangulated graph. Then we move towards vertex guard. So the position of the guards are restricted to the vertex of the polygon. So these vertex guards, and then we have the point guards. So these are guards that can be located anywhere in the polygon to be guarded. Then we have the edge guards. So guards moving along the edge of the polygon. Then we have the mobile guards. The guards are allowed to move along closed line segments totally contained in the polygon. So what are the applications of art gallery problem? Basically, the most important application of art gallery is nothing but security in art galleries, museums and hallways. Now let's move forward. The art gallery problem is a NP-hard problem. What does that mean? In computational complexity theory, NP hardness is the defining property of a class of problems that are informally at least as hard as the hardest problem in NP. A common misconception is that the NP in NP hard stands for non-polynomial, when in fact it actually stands for non-deterministic polynomial acceptable problems. So people suspect that there are no polynomial time algorithms for NP-hard problems, but that has not yet been proved. So this is NP hardness, and art gallery problem is a NP hard problem. Now let's learn some important points from a survey paper on art gallery problem, that is the art gallery problem status and perspectives. So, the art gallery problem was first posed by Victor Klee in 1973 for stationary guards. So, Vasek Chwatal gave proof for the art gallery problem in 1975. He came up with a theorem and he said that n by 3 stationary guards are always sufficient and occasionally necessary to illuminate a polygonal art gallery with n vertices. The method proposed by Vasek Chwatal depended on fan triangulation, which basically means triangulation by selecting one vertex, which is the fan center, and then drawing the diagonals to other vertices to form a triangle. But the disadvantage of this method was that it could only be used for convex polygons, whereas in the real world 99.9% polygons are non-convex. Then later in 1978, Steve Fisk proved the same result using coloring method. The graph of triangulated polygon can be 3-colored such that no two adjacent nodes are assigned the same color. Then place the guards on those color nodes which have fewer occurrences to get minimum guards. We can see the figures. Now let's talk about polygon with holes. Polygon with holes. We can see the example in the slide of a polygon having three rectangular holes in it. So O'Rourke in 1987 gave a theorem that any polygon with n vertices and h holes can always be guarded with n plus 2h divided by 3 vertex guards. So a method of choosing cuts which uses dual of a triangulation was mentioned by Rauke, which guarantees a single polygon at the end. The important part of the proof, however, is that after all holes are cut, the resulting polygon would have n plus 2h vertices. This is because each cut would produce two new vertices. As now we have a single polygon without holes, apply the classic art gallery theorem, which gives the desired result of n plus 2h by 3 vertex cards. Then later, another theorem was given by Jorling, Sachs and Sauvien for polygon with holes using point guards. Now the first algorithm was for vertex guards now, and the second algorithm is for point guards. It said that n plus h divided by 3 point guards are always sufficient and occasionally necessary to guard any polygon with n vertices and h holes. They first connect each hole to the exterior with a quadrilateral channel, making the polygon hole free as holes have been merged with the exterior. The channels are such that only one new vertex is introduced for each channel, and a triangle in the remaining polygon sees all of the channels. Then they triangulate the whole free version of the polygon while ensuring that this triangle exists in the triangulation and place guards based on 3 coloring. Orthogonal art gallery. So orthogonal art gallery is a variant of normal art gallery in which all the polygons are orthogonal in nature. In 1983, Kahn, Clive and Kleitman gave a theorem that for orthogonal polygon with n vertices, n divided by 4 vertex guards are always sufficient to guard it, and there exist polygons where n by 4 vertex guards are necessary. The method they tried using was partitioning the orthogonal polygon into convex quadrilaterals and then applying 4 vertex coloring method like the 3 vertex coloring method. Then another theorem was given by Frank Hoffman and Klaus Kreisel in 1993, and the theorem was n by 3 vertex guards are always sufficient to guard an orthogonal polygon with holes. And the method they used was simply converting the quadrilaterals into triangles and then further finding the solution. So now let's look into another paper of approximation algorithms for art gallery problem in the polygons. So this paper gives algorithm for vertex guards and finds the solution to art gallery problem. And I'll just explain you the algorithm and the method. So in the algorithm, what they do is they compute convex components, then they find the vertex which can guard maximum convex components. Then they find a convex component that are unguarded by the previous vertex. Then they find another vertex to guard remaining convex components. And then they keep on doing this until all the convex components are guarded. So this is very simple algorithm, and we can see the illustration of the algorithms in the figures. The time complexity of this algorithm is for simple polygon, the algorithm takes O(n) to the power 4 time to solve the problem for vertex and edge guards, whereas the time complexity for polygon with holes is n to the power 5, and the size of the solution is log n. Now this is another paper which talks about approximability of guarding weak visibility polygons. Now what are weak visibility polygons? So a polygon P is said to be a weak visibility polygon if every point in P is visible from some point of an edge. And then this algorithm mentioned in this paper uses the concept of shortest path tree. Now let's look what is this shortest path tree. So a shortest path tree of P rooted at any point S of P, denoted by SPT, is basically the union of Euclidean shortest paths from S to all the vertices of P. Now this union of paths is basically a planar tree rooted at R, which has n nodes, namely the vertex of the polygon. You can see the dotted shortest path tree in the figure. Now intuitively, the paper uses the concept of Euclidean shortest path trees from U and V for choosing vertices for placing guards. So for example, let P be the simple polygon which is weakly visible from its edge UV. Suppose a guard is placed on every non-leaf vertex of SPTU and SPTV. It is obvious that these guards see all points of P. However, the number of guards required may be very large compared to the size of an optimal guarding set. In order to reduce the number of guards, placing these guards on every non-leaf vertex should be avoided. So now let A be a subset of vertex of P and let SA denote the set which consists of parents PUZ and PVZ for every vertex Z belonging to A. Then A should be chosen such that all vertices of P are visible from guards placed at vertices of SA. And then this algorithm above presents a method of choosing A and SA, in which the first three steps are basically initialization. Then from step 4 to 11, they run a while loop until Z becomes equal to V. And then Z is initialized to U in step 3. Then Z is set to the vertex next to Z in clockwise order on a boundary of P from vertex P to another vertex Q, which is denoted by BDCU, V in the fifth line. If Z is unmarked, then add Z to A and the parents of Z to SA. Now place the guards on the parents position, that is PUZ and PVZ, and then mark all the vertices of P that become visible from PUZ and PUV. So this is the algorithm. So the main algorithm is for guarding all vertices of polygon. Further in the paper, other variants have been proposed. For example, the algorithm for guarding all points of the polygon, placing vertex guard in the orthogonal weak visibility polygon, and etc. And so the time complexity is n square for this algorithm. So before moving to the next research paper, let's see some variants of art gallery problem. So art gallery problem with fixed guard candidates is the first variant. In the art gallery problem with fixed guard candidates, that is the AGPFC, we are given a finite set of possible guard positions that are denoted by C, which belong to S, where S is the finite set of points in the polygon, and we are required to find minimum guards in C which cover the whole polygon. Then the second variant is art gallery problem with witness, that is AGPW. So here we are given finite set of points W belonging to P, and we find minimum number of guards to cover the set W. Note that covering W does not imply coverage of the polygon. Remember that a polygon is called witnessable if there exists a finite witness set W in the polygon such that any set of guards that covers W also covers P. Then the last variant, which is the hybrid of these two and brings sufficient amount of discretization to the problem in art gallery problem with witnesses and fixed guard candidates, where both the points to be covered W and the potential guard position C are finite. This problem can be cast as a set cover problem, that is SCP, where elements of W are to be covered using subsets of witness points visible to each guard in C. So basically, set cover problem is a possible solution to all these three variations of art gallery problem. So now let's talk about our fourth paper on art gallery problem, the quest for optimal solutions for the art gallery problem, a practical iterative algorithm. So as a matter of fact, as recently as 2017, experts have claimed that practical algorithm to find optimal solution or almost optimal bound are not known for art gallery problem. So this paper tries to find some optimal solution. This paper presents a practical iterative algorithm for the art gallery problem with point guards, which finds a sequence of decreasing upper bounds and increasing lower bounds for the optimal value. This paper gives a solution to AGP by solving other variants of AGP in the algorithm as seen in the previous slide. So these variants are the art gallery problem with witness, art gallery problem with fixed guards candidates, and the art gallery problem with witness and fixed guards candidates. So there are some important terms that we need to look into before we move further. So first important term is the visibility polygon. So visibility polygon of a point P denoted by vis P is a set of all points in P that are visible from point small p. The edges of vis P are called visibility edges and they are said to be proper if and only if they are not contained in any edge of P. Now, given a finite set S of points in P, a maximal connected region called a covered region induced by S in P. So this S set induces an covered or uncovered region into the polygon. Now, another important term is the atomic visibility polygons. So the geometric arrangements defined by the visibility edges of the points in S partition P into a collection of closed polygonal faces are called atomic visibility polygons. So basically in this algorithm what they do is they initialize a witness set D, then form the arrangement defined by visibility edges of the points in S and then use the light AVPs for finding the solution to art gallery problem with witness. And then further by updating the witness set, they find solution to another variants of AGP, that is the art gallery problem for witness and fixed guard candidates. So this is how the algorithm works. We can see in these figures, the left on the top right, the left figure shows the initial witness set, the center figure shows the arrangement D and the AVPs, that is the light AVP is the white boxes and the black AVP is the black polygons or boxes. And on the right we have the solution to AGPW. Below on the left we have updated witness set and on the right we have the solution to AGPFC and AGPWFC. So for this research, the computational experiments were done on 1440 different polygons. In the table, optimality rate, average time taken by the algorithm to run, and the number of minimum guards were compared for given algorithm and other prior algorithms from other researchers. It can be clearly seen that the proposed method in this paper gives better results on all computational aspects. So basically the optimality rates. So optimality rates should always be higher. In this case, this paper has highest optimality, that is 100%. Then the average time should always be lower, and we can see this algorithm given in this paper have lower time as compared to the prior methods, and we can see that in the table. Then the number of guards, and the number of guards should always be minimum. So the number of guards are also comparable and a bit less than the prior methods. Now let's compare the three algorithms mentioned earlier. So the paper 2 was basically the approximation algorithm for art gallery problems in polygons. Paper 3 was the approximability of guarding weak visibility polygons, and paper 4 is the quest for optimal solutions for the art gallery problem, a practical iterative algorithm. So the polygon type for paper 2 was polygon with and without holes. For paper 3 it was polygon without holes, and for paper 4 also it was polygon without holes. So type of guards in paper 2 were vertex, and edge guards. In paper 3, the guards were vertex guards and point guards, and in paper 4, they were point guards. So time complexity in paper 2 for the algorithms for polygons without hole was n to power 4, and for polygons with holes was n to power 5. In paper 3, the time complexity for polygon without holes was n square. And for paper 4, it was better than spending n log n for computing n by 3 guards. And space complexity for paper 2 was log n, and it wasn't mentioned in paper 3 and paper 4. The advantages of paper 2 were that paper 2 gives a solution to both polygons with and without holes, whereas paper 3 has low time complexity, and paper 4 gives best optimality rates and evidence for real world implementation. So based on what we observed, the paper 4 can really be implemented in the real world, but we are not sure if paper 2 and 3 could be implemented. So therefore the disadvantage of paper 2 is that it has high time complexity and it is difficult to implement in the real world scenario. Paper 3 has disadvantage of I mean, it is of course also difficult to implement in real world scenario, and no algorithm was given for polygon with holes in paper 3. And the disadvantage of paper 4 was that again no solution to polygons with holes. So now that we have seen 4 different research paper, 1 survey research paper, and 3 different implementation algorithm research paper, here are some of the open research questions for art gallery problem. Now, instead of placing guards anywhere in the polygon as point guards, can we force the placement of these guards on some defined geometry such as the dual tree of the polygon, Voronoi diagram of the polygon, skeleton of the polygon, or shrink profile of the polygon to improve the visibility? We think visibility of the guards can be increased if we place them on such defined geometry. Another question was, so the paper 4 gives an algorithm to solve art gallery problem exactly. What is the measure of exactness? The other than experimentation results, how can we, I mean, define an exact solution? So the paper doesn't show what it actually means when they say exact solution. Another question in paper 2, solution to art gallery problem involves conversion of polygon into convex components. How will this algorithm perform in more real world scenario with too many vertices of polygons? Another question was, how will the algorithms, that is all the algorithms and their computational complexities will change when the holes in the polygons are dynamic in nature? So this is another area of research when the holes are dynamic in nature. And the final question is, can the algorithms, that means all the algorithms, improve their solutions by using dynamic guards or mobile guards instead of stationary guards? So I believe they do increase, but for implementing mobile guards in real life, they cost more than static guards. So now we have seen what art gallery problem is and how the research is, what is the status and perspective of the research in art gallery problem. Now let's move further to Shreyas, who will explain us the traveling salesman problem. Thank you.
Hello everyone, I'm going to talk about the traveling salesman problem. Let's get into it. So the traveling salesman problem is a problem to find the best, shortest suitable path by a salesperson such that it visits the n cities and so that we can reach each and every city exactly once and finally come back to our initial position, and we want to find the shortest path as well as using the least amount of time. If we were to represent that in a graph, that would be given by let g equals to n comma e, where n is the number of cities and e is the number of paths between the cities. Then we can calculate the cost matrix by applying the Euclidean distance between the two cities. And the traveling salesman problem is broadly recognized as NP hard problem. This implies that there is no solitary algorithm to solve it in polynomial time, and the widespread use of TSP are sharing systems, system sharing of items or assets, discovering shortest track, planning traffic lights, etc. Let's look a little bit more into the applications. So these are the applications, few of the applications that I've written over here. There are plenty more. The applications of traveling salesman problem trace back as far as 1940s, where it was first discovered for using transportation and logistic applications during the World War. And then subsequently after the World War, people tried to make use of it to find economic boom. Traveling salesman problem can also be used for scheduling a service call at cable firms, managing flights, applications in crystallography, drilling holes for electric circuits. For example, if you look at motherboard, there are a bunch of lines that you see. These scan chains are routes included on a chip for testing purposes, and it's useful to minimize their length for both timing and power reason. These are the other advantages. I'm not going to go too detailed into them, but these are just to show that traveling salesman problem has a large amount of scope of research and not just for planning path. It's used in different fields as well. I'm going to talk about three different algorithms to solve traveling salesman problem. The first one that I'm going to talk about is solving traveling salesman problem using ant colony optimization. And as I said before, the best known method to solve TSP is a NP hard problem, and the best known exact methods to solve for TSP include enumeration, branch and bound methods, cutting plane method, and dynamic programming. However, these methods work well for smaller scale problem. Whenever you try to increase the number of nodes, these problems increase in exponential NP um, problem and lead to a large amount of time and resources being used. Thus, we need a better solution. So this paper came up with ant colony optimization paper. Heuristic methods vary from exact methods, and in that they give no guarantee to find optimal solution to the given problem in given time. But in many cases, the solution is good quality or suboptimal within the optimal time. So we may not get the most optimal solution, but we get a suboptimal solution which is good enough within the given time and resources that we have. And the significant part of heuristic comprises of meta-heuristic methods, which differ from the classic methods in that they are combined with stochastic and deterministic composition. It means that they are focused on global optimization, not only for local extremes. And the big advantage of this meta heuristic is that they are built not only for solving concrete type of problems, but they describe a general algorithm in that they can be used for any type of problem to become a solution of the problem. This is what we call the black box procedure. In this paper, they explain the algorithm is such that the ants always find the solution at the start, which is suboptimal, but good enough and guarantees food for the ants. However, what is important is that the movement of the ants is not deterministic. What I mean by that is that few of the ants will keep on using the non-preferred path and look for another best solution. Basically, it's a balance between exploration and exploitation that we saw in class, where we try to parameterize alpha and beta and try to find the balance between exploration and exploitation. Every ant has its own memory, which is used for saving information about the travel path. For example, the travel nodes. This memory can also be served to ensure that constraints or to ensure that we have the constraints appropriately used or to evaluate the solution. If you look at the also pheromones are chemical substances which attract other ants for searching the food. This is basically uh, the reason why ants go out of their place to find food, and pheromones are basically the food or chemical substances which attract the food. And each ant, whenever it finds the food, it leaves some percentage of pheromones on the edge of the graph. The quality of the solution depends on the number of ants. If you look at this table over here, we can see that for 1000 iterations, when the number of ants is 100, the solution is found. It's a suboptimal solution, uh, which is um, uh, which is found which for m equal to 100, the difference is 17% in the optimality from the optimal solution. For m equal to 1000, the difference is 11.56%. Just so in case I didn't mention it, m is the number of ants being used to solve the problem. For m equal to 5000, the difference between the optimal solution and the found from the exact methods and the and colony optimization, the difference is 5.44%, and for m equal to 10,000, the number of ants, the difference is less than 1%, which is 0.83. This method has advantage over the exact method that it can solve the problem much faster with a good enough solution. However, this is also a problem um, which can lead to which may not be ideal in higher TSP, higher level, higher dimension TSPs. Also, ACO converges prematurely if the number of ants are low and sometimes becomes stagnant, which is a research concern that needs to be answered. Next algorithm that I'm going to talk about is solving traveling salesman problem using the genetic algorithm. This There are five things that we need to know in genetic algorithm. But first, let's talk about the general approach in genetic algorithm. Um, it basically involves generating a random size population, which is called the gene pool. Then the best genes are chosen as the parents, and our best two genes or three genes depends on how that's a hyperparameter that can be tuned, and they are mated, and newly created genes are the children added to the population. Let's look at what encoding, evaluation, crossover, mutation, and decoding means. Encoding is a suitable encoding which is found for the solution to the problem so that each possible solution has unique encoding, and encoding is some form of a string. Evaluation is the initial population, which is selected usually at random through alternative techniques using heuristics that have already been researched or proposed in prior papers. And the fitness for each individual in this population is computed. That is, how well the individual fits the problem and whether it is the near optimum solution compared to the other individuals in the population. Crossover. Crossover is the fitness used to find the individual probability of crossover. Crossover is where the two individuals are recombined to create a new individual which are copied into the new generation. Basically, what I mentioned at the start of the algorithm. Um, Mutation is something that is used to get out of in case we get stuck in local minima. Uh, Mutation occurs when some individuals are randomly chosen to be mutated, and then a mutation point is randomly chosen. Basically, some characters are changed and something randomly, a new child is generated, which could result in a better solution. Kind of like how in the ant colony optimization, the ants always go in a trying to find the different path. Mutation is similar to that. It's based on probability. Um, Also, in each iteration, elitism is used to save the best gene from the previous population. This is to ensure that if we were close to the previous solution with the fitness value, and after a new population is generated, we do not want to lose the last closest solution. So, elitism saves the best gene from the previous population and adds them to the population. um, Decoding is once all of this is done, a new generation that has been formed, um, and the process is repeated until some stopping criteria has been reached, which is whether the number of iterations or the time limit. And at this point, the individual which is closest to the optimal solution is decoded, and that is considered to be the solution of the problem. This flowchart basically explains what I was trying to say. First, we create an initial population, then we select by fitness function. Then we select the parent population having fitness value closest to the threshold. If the criteria is satisfied, then we stop. If it's not satisfied, then we select two strings and from the population perform crossover, make offspring, and then the mutation is not mentioned here, but there should be one mutation branch over here as well, which will again add one more offspring and add to the population. Um, this is basically the whole idea of survival of the fittest law, where in nature, if you look, many animals have evolved due to the drastic changes in the nature. Polar bears, for example, were normal bears, but due to the ice and in the Atlantic, in the Arctic, they have evolved their fur and they go into hibernation. This is a similar idea where the only the best gene survives from the population. I'd like to mention a thing about fitness function. Fitness function is problem specific, and in this case of traveling salesman problem, generally fitness function in genetic algorithm refers to maximizing something. Here we are trying to minimize the path found, so the fitness function here is inverse of what we normally use. let's look at results and comparisons for genetic algorithm with the dynamic programming or the brute force methods. If you look at this table, you'll see that the time complexity for genetic algorithm is exponential. Um, and the best solution is found using fitness criteria. However, it's not an optimal solution, it's an approximate solution. When it comes to greedy solution, it is definitely the fastest solution, but it may get stuck in a local optima, local minima, and there's no guarantee of solution. In dynamic programming, um, the time complexity is shown over here, o big O of n square and 2 times 2 raised to n. It finds the global optimal solution, but it is very expensive for both memory and time, and that is considered to be the biggest drawback. The biggest one of the drawbacks of genetic algorithm is that genetic algorithm appears to find good solution for traveling salesman problem. However, it depends very much on the way problem is encoded and which crossover and mutation methods are used. Basically, these hyperparameters are the problem specific and need to be tuned for each problem, which is a big drawback for the TSP using GA. It's not a general algorithm. You have to tune the hyperparameters. Perhaps this problem can be solved by applying reinforcement learning or deep learning to find optimal parameters. This is one. This is one of the biggest drawbacks, and which is covered in the next algorithm, which is to solving the traveling salesman problem using the particle swarm optimization algorithm. This algorithm overcomes the big issue of genetic algorithm, which is tuning of hyperparameters. Uh, they work on the same principle of having a population, but the PSO optimizes the population through information exchange between individuals, kind of like how reinforcement learning works. And the biggest advantage PSO has over genetic algorithm is that its convergence speed is very, very high compared to PSO. And this was confirmed in this paper by when they applied GA and PSO for four different fitness functions, which are the Schaefer function, Schubert function, Hansen function, Camel function, and each of them showed that PSO was faster to converge than the genetic algorithm. Um, this fitness function is again problem specific, and for traveling salesman problem, fitness function is defined as 1 upon summation of 1 to n is the number of cities, the distance between the current city and the next city, and that divided by mod of n. um, PSO is an algorithm which was first presented in 1995 by Ebhart and Kennedy, and it was developed under the inspiration of behavior of laws of bird flocks, uh, fish schools, and human communities. It is also a meta heuristic, as it makes few or no assumptions about the problem being optimized and can search very large spaces of candidate solution. However, since it's meta heuristics such as PSO, it does not guarantee to find an optimal solution. It will find a solution. It will just be a suboptimal solution. Let's look at the algorithm. In PSO, each optimization problem solution is taken as bird in the searching space, and it is called particle. Every particle has a fitness value which is determined by target functions, and it also has a velocity which determines its position, its destination, and distance. All particles search in the solution space for their best position and the position of the best particles in the swarm. And PSO is initially a group of random particles, just like how it is in genetic algorithm. And then the optimum solutions are found by repeated searching. In each iteration, a particle will follow two bests to renew itself. The best position found for a particle called the best P, and the best position found for the whole swarm called best G. All the particles will determine the following steps through the best experience of individual themselves and their companions. Let's look at the results or the comparisons between PSO and GA. I mentioned that PSO is much faster than GA. That is proved by the convergence proof for the four functions that I mentioned before. If you look at table 1, um, table 1 shows that for 100 iterations, PSO converts 75 times, whereas GA converts 72 times. For second function, it converts 80 times, whereas GA converts 75 times. For the third function, PSO converts 90 times, whereas GA converts 85 times. and for the final function, PSO converged 56 times and GA converged only 23 times. Um, for the traveling salesman problem, um, they ran the test cases for Berlin 52, which is a known key test case, and the number of cities vary from 52 to 1432 as shown in the table. And the optimal solution for these cases have already been found in the TSP library, and they compared the genetic algorithm and the PSO with the optimal solution found in the TSP library, and we could see that uh, even though up till 400 cities, GA and PSO found optimal solutions. But as the time complex as the number of cities increased, it converged quickly or prematurely converged and led to a suboptimal solution. However, the solutions were always better than the genetic algorithm. Uh, However, this is also considered to be a drawback since it's always going to give a suboptimal solution. Let's look at the comparison between the three algorithms. The first algorithm, which was the ant colony optimization, it can adapt to changes in real time. Suppose for some whatever reason, the traveling salesman tries to go to one factory and that factory is suddenly closed or being um, is not available. Ant colony optimization can adapt to it really quickly because it makes use of the explore exploit parameters. However, one of the it has various disadvantages. One of it is being because you have to tune alpha and beta. If alpha is -1 or negative, it can stagnate in suboptimal solution, meaning that no matter how many iterations you do, it will always find the same solution or get stuck in local minima. You again have to tune the hyperparameters of alpha and beta, and the convergence speed depends on the number of ants. In genetic algorithm, it does not always get stuck in local optima. Oh, sorry, it does not get stuck in a local optima. It will always find a solution um, given the crossover rate and mutation parameters are set properly. However, that is again the biggest drawback of this method, that you have to hypertune the parameters of elitism, crossover rate, culling rate, mutation rate, which makes it a problem specific algorithm. Um, in PSO, its biggest advantage is that it has very fast convergence rate compared to genetic algorithm and ACO, and again, and it also does not get stuck in local optima. However, PSO as well as the other algorithms fail to work in high dimensional problems, as is the and it will again find suboptimal solution and not the optimal solution. Some research concerns in traveling salesman problem include um, all the algorithms that presented for TSP are definitely efficient in terms of space and time compared to the conventional method. However, they do not provide an optimal solution for the bigger TSP problem. Perhaps a hybrid solution involving a global panel with the genetic or PSO or the ACO algorithm, and maybe using conventional algorithm for local planning can help improve the solution. That is one area of research that can be worked on. Another is, um, as the problem mentioned, the ACO has the issue of stagnation, genetic algorithm has the issue of premature convergence and suboptimal solutions. For higher degree, it's the problem for all three solution. And um, as we this is something I came up with. I'm not sure if this has been done in the research before, but perhaps in the local planner we can make use of the KD tree that we learned in class to find the nearest neighbors, to find the pair of neighbors to connect. um, it may not always find the solution, but it should be still be better than using the local conventional local planners. These are the references that we have used. The first four references are for the art gallery problem given by Ritik, and from 5th to 8 are the references for traveling salesman problem. Thank you. Any questions?